Hey everyone, Mr. Fransky here again. One more piece to this puzzle that is 2.4, and that is the rational roots theorem. And so the last problem I did in the last video where we were putting everything together involved something where I gave you two roots. I gave you x equals 1 and x equals -1. And in this one, we're going to explore what happens if you're not given any roots, because we only know how to factor a quadratic. We can't really factor anything bigger unless it was like able to use grouping or chunking or something. But there is a way to just kind of start guessing roots and to do it logically and get a good result with what you're trying. So rational root theorem, today we're going to be able to use rational root theorem in conjunction with division techniques to find all the zeros of a polynomial. So let's jump in and see if we can do that. Vocabulary today: dividend, divisor, quotient, remainder, stuff we've seen before. We're also going to talk about the rational roots theorem. Okay. So find the zeros by factoring. Notice anything about the relationship between your answer and the original problem. So to factor this, I would first pull out a 4. And then I'm left with x squared minus x minus, what is that, 6? So we can factor that. It's x and x. I have to think what multiplies to -6 and adds to -1. Well, 2 and 3 will add to 1 of some sort. I need -3 and a positive 2. Then I get -3x, positive 2x. So the zeros here are x equals -2 and x equals 3. Now, the reason I asked if there's a relationship between your answer and the original problem, -2 and 3, if you multiply these together, what do you get? Well, you get -6, right? -6 actually comes from something in the problem. It comes from the last term divided by the first term. -24 divided by 4 is equal to -6. Now, this kind of happens every time because if you think about where the x-intercepts are going to happen, they're always going to be the numbers that multiply to this last number over here, right? Especially after I pulled out the leading coefficient, I ended up with that -6 at the end. That is the product of the roots. So if I know that, let's call our roots C1 and C2. So if you have a quadratic, right, x minus c1 and x minus c2, you must be able to write it this way after you pull out any leading coefficient that you have. So c1 times c2 is always going to be equal to like that last term divided by the first term somehow. In this case, it would either have to be 6 times 1, like 6 times -1, -6 times +1, could have been 2 times -3, or it could have been -3 times 2. Now notice there are not a lot of choices there, right? And this happens for anything. It doesn't matter how long the polynomial is, because if I had more roots, like c1 times c2 times c3 times c4, it doesn't matter. Whatever I have, they're going to have to end up multiplying to that last number, dividing by the leading coefficient. So we're going to use this property to our advantage, what's called the, rational roots theorem, Fransky. Rational roots theorem. So here's what the rational roots theorem says. If you have a polynomial, so if you have a polynomial p of x, we've seen it written this way before, an x to the n, an minus 1 x to the n minus 1, an minus 2 x to the n minus 2. All we're saying here is the exponent's decreasing, and each one of these constants are different, right? The reason we can't use like x, y, z, or a, b, c, or something like that is because maybe there's more than 26 terms, right? So we keep doing this, and then eventually we end up with a2x squared plus a1x plus a0. So that's our constant at the end. So if you have this polynomial, then every rational root, so this is important, right? Because like if you have like x squared minus 5, x squared minus 5 has no rational roots, right? The roots of this are root 5 and -5. Okay, so this is not going to work on something like that where we have irrational roots, but every rational root is going to be p over q, where p, so rational means it can be written as a ratio of two integers, right? Where p is a factor of the last term, a0, and q is a factor of the first term, an. Okay, so really the strategy you use here, oh, come back to me. Oh, go away. Sorry, guys. There we go. Hello, Ella. Come back here. Sorry about that. So, the strategy we're going to use here The strategy we're going to use is we just list all of the factors of the last term. So factors of the last term. And we always have to do plus or minus on each one of those. And we divide by plus or minus the factors of the first term, the leading coefficient. And then we're going to try every combination. Try every combination. And what do we know about our roots? If we plug them in, what should they give us? If we have any root, when we plug it in, it should give us 0, right? So try every combination of the factors of the last term divided by the factors of the first term. And this will give you every possible rational root. Okay? And what we're going to do is we're going to use synthetic substitution on this. So use synthetic, you call it division or substitution, either one. We'll call it synthetic substitution. And our goal is to get down to a quadratic, because once we're down to a quadratic, we can either use a quadratic formula or we can use factoring to be able to figure out the rest of it. So use synthetic substitution to get to quadratic. Once we're to a quadratic, we can use those other strategies. So let's take a look at an example with this. So find all rational zeros of f of x equals 3x cubed plus 4x squared minus 5x minus 2. So what we do is we say, well, any rational zero is going to have the form. I just list out all the factors of the last term divided by the factors of the first term. So all will have the form plus or minus, so let's list factors of 2. It could be 1 or plus or minus 2, right? Those are the things that multiply to make a 2, divided by plus or minus 1 or plus or minus 3. So now I always list out all the roots. If you don't list out all the roots, then, or the potential roots, then you'll probably miss one. So I always do the easy ones first, right? So 1 over 1 could be plus or minus 1. 2 over 1 could be plus or minus 2. So I always list out the integers first. I think it's easier that way. Or it could be plus or minus 1/3. Or it could be plus or minus 2/3. Okay. So now I have a list of all the potential rational roots. Those are the only ones it could be because they have to be factors of -2 divided by factors of 3. Has to be. That's what rational root theorem says, because if you pull out the 3, what would we have left? X cubed plus 4/3 x squared minus 5/3 x. Those middle terms don't really matter, but then minus 2/3. This last thing is what matters, right? Whatever's multiplying has to end up making that 2/3 happen at the end, right? So it's probably going to be one of these thirds over here and probably one of the constants. So I always start with the easy ones. Okay, so let's try a positive 1 first. I put 1 into my box, and I'm going to try to get a remainder of 0. So we have 3, 4, -5, -2. And 3 comes down, times 1 is 3, plus 4 is 7, times 1 is 7, minus 5 is 2, times 1 is 2. Hey, we found one right away. Look at that, right? Now, it doesn't always happen. You're going to find probably that you'll struggle through some of these where you have to try like 3 or 4 of them before you get to the one that's going to work out. But I always start with the easy ones first. So 3, I just want to make sure it's actually worked. Yep, 2, yep. Okay, so what I know now is that f of x is equal to x minus 1 times 3x squared plus 7x plus 2, right? Because we get those those coefficients from the bottom of the synthetic division right here. So now let's see if we can factor. So because we now have a quadratic, so I can see if I can factor the rest of it. So we have x minus 1. Let's do 3x and x. Only way to make 2 is 2 and 1. Let's see if I put a 2 here and a 1 here, I get a 6 and a 1. Yeah, 7. So it looks like irrational roots are x equals 1, x equals -1/3, and x equals -2. And were they all on my list? Here's 1. Here is -1/3. Yep, that was on my list. And here's -2. They were all on my list. Nice. And if you multiply them together, -2 times 1 is -2 times -1/3 is 2/3. So we get that last term. Nice. This time we have a quartic, which means we're going to have to find 2 roots before we can factor, right? Because our tools that we have now is the rational roots theorem. That can find any rational roots, and hopefully we find 2 of them. Because if we find 2 of them, we'll divide them out using synthetic division, and we'll end up with a quadratic left. Because every time we take 1 away, it takes 1 off of our degree. And then we can, so after we use synthetic division to get down to a quadratic, then we're going to be able to factor that, or use quadratic formula, or some other way to be able to find those last 2 zeros. So let's start out by listing our potential factors. So we're going to have factors of 8. Factors of 8 divided by factors of 2. Always remembering the plus or minus. So we plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. On the bottom, plus and minus 1, plus or minus 2. That's it. So our list of potential roots, we could have anything over 1. So plus and minus 1, plus and minus 2, plus and minus 4, plus or minus 8. Now we had some repeats. 2 over 1 is 2. We already have that. Right? Sorry. Sorry. 1 over plus or minus 1/2. I look at the wrong spot. 2 over 2 is 1, though. We already have that. 4 over 2 is 2. We already have that. And 8 over 2 is 4. We don't have to list things twice, right? So we have 2, 4, 6, 8, 10 possible roots. Hopefully we don't have to go through all 10 before we find them. But let's give it a shot. We have 2 we have to find, so we should be able to find them before we get to the end. So let's start with 1. List our coefficients. 2, -7, -8, 14, and 8. Line down here. 2 comes down. Times 1 is 2, minus 7 is -5. Times 1 is -5, minus 8 is -13. Times 1 is -13, gives me a 1. Times 1 is 1. Nope, that adds up to 9. We have a remainder. So I'm going to use some digital magic here. We're going to use our same coefficients, so I'm just going to kind of save that. Good problems to do on your desk with a whiteboard marker because you can erase them, do them again. So let's try -1. So we tried +1, we're trying -1 now. Always start with the easy ones. You don't want to start with 1/2 if you don't have to, right? So 2 times -1 is -2, -9, +9 minus 8 is 1, times -1 is -1, 14 and -1 are 13, -13, nope, no good. Does not make 0, right? Because we're trying to make 0, because if we get a remainder of 0, that by factor theorem tells us that when we plug it in, we make 0, which makes it an x-intercept. So let's try a 2. 2 times 2 is 4, minus 7, -3, -6, -14, getting really big, negative, +14, 28. Nope, that's not going to work. As soon as you see it's not going to work, you can just get rid of it. Let's try -2. 2 times 2 is -4, -11, +22, getting pretty big here. I don't like it. Minus 8 is 14, times -2 is -28, and 14 are -14. Nope, that's going to be a big positive number, plus 8 will not make 0. Okay, let's try 4. 2 times 4 is 8, minus 7 is 1. I always get excited when the numbers are small, because I'm like, maybe we have a shot. Times 4 is 4, minus 8 is -4. Times 4 is -16, and 14 are -2. -8 makes a 0. There we go. So what have I just shown? Let's make a list of our roots and our factors. So the root we just found was 4, which means the factor is x minus 4. So what I know now is that f of x is equal to, x minus 4 times our result down here, 2x cubed plus x squared minus 4x minus 2. Okay, good. So now I'm going to try to keep dividing out from here. I could keep dividing from our original function, but I already know that the 4 is taken out of it. So now I'm looking for things that are factors of the resulting cubic, right? Because if I pulled the 4 out of here, that the factor is going to be the result of this cubic. I don't have to try anything I already tried because we know it wasn't a factor of the entire thing, so it's not going to be a factor of this result either. So I'm going to use these guys now, draw a new line. It'll be faster because I only have 4 things to check. And so I already tried +4. We're now on to -4, I believe. So 2 times -4 is -8, and 1 are -7. Positive 28, that's getting pretty big, not looking good. 24, negative, no, that's not going to work. Okay, let's try 8. So 2 times 8 is, actually, I can do better. Some of you might have seen this. Well, now we only have to try factors of 2 over factors of 2. So plus and minus 2, plus and minus 1, over plus and minus 1, plus or minus 2. We already tried 1 and 2, so it must be some kind of 1/2. Plus and minus 1/2. Has to be one of those, so I'm going to jump right to those. So let's try 1/2. 2 times 1/2 is 1, and 1 are 2. Times 1/2 is 1. Minus 4 is -3. Nope, that's going to give us a -3/2. That won't work. Let's try -1/2. 2 comes down. Times -1/2 is -1, gives us a 0. 0 again. -4 times -1/2 is 2. Hey, 0. That works out. So now I know f of x. I just picked up another root. Was -1/2. -1/2 is my new root. And that means that my factor there, I'm going to write it as x plus 1/2. Yep. So now I know that my my polynomial is x minus 4 times x minus a half, plus a half, excuse me. And then my resulting quadratic is 2x squared minus 4. Cool. And I think I can try to factor that, right? So I can pull a 2 out of that. So I have f of x equal to, I'm going to pull the 2 all the way to the front. So I have 2 times x minus 4 times x plus a half. And then times, I'll have x squared minus 2 left now. Right, because I pulled a 2 out of this from both of these, so we have x squared minus 2 left. So that is equal to x minus 4 times x plus a half. And now this factors to x minus to root 2, x plus root 2. And that's why those didn't show up, because they're not rational roots. Cool. So, a lot of work, but really not difficult. It's just kind of plugging these things in synthetically over and over and seeing if it works out. So, that's all I've got for you guys. Good luck on your rational root problems. They're kind of fun. I love you guys. That's why I'm here. Have a great day.